Dear friends, today we will discuss electric potential energy. Okay, I have told you when I discuss electric potential or electric potential energy, I am starting the chapter, I am bringing the concept from gravitation, because in gravitation it is easy to see the objects, but in electric when charge move then we can able to see. So let's come first try to understand what is gravitational potential energy. You have already read in class 11th, still I am just recalling what you have learnt in class 11th. So if this is suppose earth, this is your mother earth, object is here, one object of mass m is here, object is at a height h1, then you know this object has some potential energy. How much? mgh1? No. The actual potential energy you know in class 11th, minus g m mass of earth into mass of the body divided by r plus h1. R means radius of earth. Okay, just you forget that is not required here. But the body has some potential energy, gravitational potential energy when it is at a height h1. If I will take the body to height h2, suppose the body is taken now to height h2, what about the potential energy of the body? Now it increases or decreases? Okay, you know also from lower classes, when it is taken to more height, then its potential energy increases. Why its potential energy increases? From where the body gain energy? Amount of work done. When you did some work to take the body from this position to this position, the amount of work done stored in the body in the form of potential energy. Why amount of work done is stored in the form of potential energy, or why the potential energy of the body increases? Because work is done here against force. You know, gravitational force acts in downward direction, but you are taking in opposite of the force, hence its potential energy increases. But when the body will fall from this position to this position, h2 height to h1 height, what about its potential energy? Decreases. Why? The body falls along the force. So now one important concept we borrow from class 11th, when a body moves along the force of the field, means automatically moves, then its potential energy decreases. But when body moves opposite to force, its potential energy increases. Remember, this is a very important concept. The same concept also will be used in electrostatic chapter. Along the force, potential energy decreases. When move opposite to force by external agent, then potential energy of the body increases. But when you take from this position to this position, what happens? Some work is done. That work done is how much? Is equal to change in potential energy. Work done is equal to change in potential energy between these two positions. How much potential energy change happens? That is the work done. Due to work done, the potential energy change happens. That means when you will take a body from one position to another position, always we will calculate change in potential energy. We can calculate work done, and work done means change in potential energy. Is it? Yes. If it is like this, then can we calculate potential energy of a body at a particular point? Always we calculate work done is equal to change in potential energy. Can we calculate potential energy at a point? Yes, it is also possible. I have told you in potential also same thing. How can you find potential at a particular point? Suppose I will tell what is the potential of the body at this point, potential energy of the body. potential energy of the body at this position. How can we find? That is, when we bring the body from infinite to that point, because infinite is zero potential energy point. If we take from this point to this point, we will get change in potential energy, because this point has some potential energy. But when we bring the body from infinite to this point, then that is also change, but infinite potential energy is zero. Hence, that is the potential energy of this point. Okay, so what is the potential energy of this body? Amount of work done to bring the body from infinite to this position is the potential energy of the body. But it is not right. Again, what mistake again we did? Potential energy of a body. It is a wrong sentence. A body cannot have potential energy. A single body, suppose a single body is here. A single body cannot have potential energy. Then you may ask the question, sir, how this body has the potential energy? Actually, the potential energy is not of this single body at this position. Then of what? That is of system. Then who is included in the system? Your Mother Earth is included in the system. Due to Earth, the body has potential energy. That means that is the potential energy of the system, which comprises of the Earth and the body. A single body, suppose in the universe a single body is there. No Earth, no Sun, nothing. Not any stellar, not any object in the universe. Then the body is alone in the space. No force on the body. If no force, then no work done. If no work done, from where the potential energy will come? Because potential energy is nothing but amount of work done. So the body will have zero potential energy if a single body is present at a point. So whenever the potential energy term comes, it must start from two bodies of the system, and a system can consist of minimum how many bodies? Two bodies. One body is here. When I bring another body, suppose I bring here M1 mass is here, I bring another mass, then I have to do work, because this mass will apply the force. And how much work is done? That is equal to change in potential energy, if we consider between 2 points, and is equal to potential energy if you will bring the body from infinite to a point. So what important conclusion I gave you now? Potential energy of a body, it's not a valid sentence. Potential energy of a system. Whenever we tell potential energy of a body, means we hide another object which is also close to it. Generally we tell potential energy of a body in case of earth and apple. We always tell potential energy of apple. But earth is there, but we hide earth. We have to understand, due to earth, apple has potential energy. Okay, so now we'll discuss the same potential energy in electrostatic. Same thing happens, just you see, the mass I replace by charge, Q1 charge. Then this is which charge? Q2 charge. 2 point charges. Now let's discuss. Suppose this is positive charge. This is also positive charge. Both are placed at distance of separation of R. R1 to I note the distance of separation. First, this body Q1 was present here. What is the potential energy of a Q1 when no Q2 was there? No Q2, only Q1. What is the potential energy of a Q1? No charged body near it. Then already you understood, a single body do not have any potential energy. So Q1 potential energy is 0 because no force act on it. But when I bring Q2, from infinite to a separation of R12. To bring Q2 from infinite to this position, I have to do work, because this is positive, this is positive. This Q1 repel Q2 like this, but I bring Q2 from infinite to here, means against the force of repulsion. Force is to there, but I bring against the force of repulsion. So we have to do work, and the amount of work done is equal to potential energy of the, not Q2, of the system, Q1 and Q2. So whenever many number of charges are present nearby, then what is the potential energy of the system? What is the definition of potential energy then? It is the amount of work done to bring the charges from infinite. One charge will bring. To bring the charges from infinite to their respective positions to constitute the system. This is the potential energy of the system. So again I am repeating, amount of work done to bring the charges from infinite to their respective positions is the potential energy of a system of charges. Okay, let's start. Potential energy from two particle system. This one. So first to this position, which charge particle will come? Q1 will come. We will bring Q1 first from infinite to its position. When you bring Q1, what is the work done? Work done is 0. To bring Q1, work done is 0, because it is brought from infinite to this position. No work is done. No charge was there initially. No force was there. But when I bring Q2, how much amount of work done? What is the work done to bring Q2? You already know that. I have done this derivation in the previous video, that when I bring, while deriving the potential due to a point charge, you just recall, while deriving the potential due to a point charge, when I brought Q2 to distance R separation, while calculating potential due to a point charge. Okay, what was the work done there? K Q naught by R. You just see, I have already derived the work done expression. Just a similar expression I will put here. I am bringing Q2. In place of Q naught I am bringing Q2. In place of Q, here is Q1. So what is the work done? K Q1 Q2 by R 12. Similar to this. Okay. So this is the work done to bring Q2 near Q1. Then what is the potential of the system? Total work done W1 plus W2. So this is 0 plus this K Q1 Q2 by R12. So this is the potential energy of a two particle system. Have you applied this formula anywhere? Yes, you have applied. Where? You don't know, but you have applied this formula in chemistry in 11th class. You just recall, here is the nucleus and here is electron revolves around the nucleus at a distance r. Your chemistry teacher has calculated the total energy of the electron, kinetic energy. You know that half mv square you put. But potential energy, now you see the potential energy expression of this system. This system consists of two particles. One is nucleus plus Z, one is electron minus C. Then what is the potential energy? Formula is here. You just put this formula for two particle system. K Q1 Z Q2 minus E divided by R. You remember, if charge is minus, you have to take its minus sign like potential. Okay, if charge is plus, you have to take its plus sign. Then now in place of K, if you put 1 by 4 pi epsilon naught, this is ZE square by R with a minus sign. This is minus. And why the potential energy is coming as negative? What is the significance of this negative sign? Force is attractive. I have told you potential negative means force is attractive. Here negative potential energy means force is attractive. You have done this expression in chemistry in class 11th, but you wrote this expression directly, but now you understood from where the electron has potential energy. Okay, so now you go potential energy of 3 particle system. If I add one particle here, 3 particle system, now you see this is R1 3, this is R2 3 distance. Then again we'll start the same procedure. To bring Q1, what the work done? W1 0. To bring Q2, what the work done? W2 K Q1 Q2 by R12. First we bring Q1, then we will bring Q2. Okay, Q3 was not there, so only one work is done to bring. When Q2 is brought, it is brought against Q1. But when we bring Q3, what happened? Earlier how many charges present? Already 2 charges are there. One is Q1, one is Q2. When I bring Q3, I have to do work against Q1, I have to do work against Q2. How many works I have to do? 2 works. Because when Q3 is coming, 2 charges are there from the starting. Okay? So now see, again another work also we have to do, that is W3. 2 work we have to do. One is Q3 is coming against Q1, R31. Another work is Q3 is coming against Q2, that is R23 or 32. So this is the W3 expression. Then what is the work potential energy of the system? Now W3 you have to add. If you add now, 2 terms are added here. Q1 Q2 Q3 by R23, then Q1 Q3 by R31. So this is the expression of potential energy due to 3 particle system, and you have to remember this expression. You have to remember. Okay, it's very easy to remember. 1 Q1 Q2 Q1 Q3, then Q2 Q3. One charge will be attached with another charge only once. Okay, 1 2 1 3 2 3. Very easy to remember this formula. This is the potential energy of 3 particle system. Now we come to the potential energy of 4 particle system. Similarly, if we do, then what we have to do? Now this is W3. What done to bring Q3? Now I am attaching another charge Q4. See here, Q4. This is R34. This is R24. This is R14. When I bring Q4 now, let's start for 4 particle system. Similar thing. To bring Q1, what done 0. To bring Q2, what done is this. To bring Q3, what done is this. But when I bring Q4, then what happened? W4. Means how many works we have to do when Q4 is coming. How many charges, which charges are there earlier when Q4 is coming? Q1 is there, we have to do work. Q2 is there, we have to do work. Q3 is there, we have to also do work. So now you see how many terms are coming? 3 terms will come. Q4, Q1, R14, then K, Q4, Q3, R343, then K, Q4, this is Q, 1 gun, 3 gun, then 2, Q1, Q2, this is Q2 by R24. Okay, so now 3 terms are again added there. So now this potential expression, what will be here? Again those 3 terms I have to add. So here it will be W4. K Q1 Q4 by R14. K Q3 Q4 by R34. K Q2 Q4 by R24. So this is the expression of potential energy of 4 particle system. How many terms are coming? 6 terms. And you have to also mug up this formula to solve numerical. Then you match the question, sir, how I mug up this formula? It's a consists of 3 to 6 terms are there. But it is very easy to remember, not required to mug up. It is very easy. There is skill to remember. You see 1, 2. This term 1, 2. Okay. Then 1, 3. See 1, 3. This term. Then 1, 4. See 1, 4. This term. You have to write it like this. K Q1 Q2 by R12. Q1 Q3 by R13. Q1 Q4 by R14, then 2, okay, then 2, 3, because 2 is already attached with 1, so from 2 we start, 2, 3, 2, 4, see 2, 3 term, this term, 2, 4 term, this term, okay, then 3, 4, this term. It's very easy to remember the formula. In this way you will remember this formula, 6-term formula. It's not difficult one. Okay, so this is the potential energy due to 4-particle system. You can try one question also I am giving you, or you can try from also inside the book example. You can try from the book example, a very simple question I am giving to you here. This is Q, this is Q, this is Q, this is Q. This is square. Side is D. 4 sides are present at the 4 corners of equal magnitude, plus Q, plus Q, plus Q, plus Q. Find potential energy of the system. Question will come like this. Find potential energy of the system. Okay, you can try this question at home, or this question can come also in indirect way. Calculate the amount of work done to constitute the system. Means indirectly what the question asks here? To calculate potential energy, but potential energy word will not be there in the question. Question will come, figure will give, or figure description will give. Then question will ask, calculate the work done to constitute the system. Okay, that means to calculate potential energy you will use 4-particle system formula. Then just to put the expressions, put the symbols, or put the values if a value will give here. So this is about potential energy. Now you go to find potential energy of electric dipole. Let's see. Potential energy of electric dipole in uniform electric field. Okay. Now let's see here. In uniform electric field. This is uniform electric field of intensity E. Now we find potential energy of electric dipole in uniform electric field. See, this is uniform electric field Q1, Q2. Q1, Q2. Okay. So not Q1, Q2, like put it's a dipole. So plus minus Q, this is 1, and this one plus Q. Okay. So minus Q plus Q. Why wrote like this minus Q and plus Q? So that dipole moment direction will be here, and this theta is the angle between dipole moment and electric field. But don't do the mistake, don't do this one plus and this one minus. If you do this one plus and this one minus, then the angle between dipole moment and electric field will change. It will be 180 minus theta, dipole moment will be in downward direction. Okay, so this is minus Q, this is plus Q, then this is the theta is the angle between dipole moment and electric field vector. This is a common mistake, don't do that. Okay, while writing minus Q and plus Q. How will find potential energy of this system? Theta is the angle. One question may come to your brain. Dipole has potential energy in uniform electric field? Yes. What happens when we keep the dipole, when we leave the dipole freely? How the dipole will remain? Will the dipole remain in the like this, in this position? No. Then what happens? Dipole, if you leave the dipole at this position, dipole will rotate. Will remain in its stable equilibrium position. This is the dipole moment. This is the electric field. This is the stable equilibrium position, you know. Dipole always remain like this. Okay, it cannot remain like this. If you leave, it will come to the stable equilibrium position. But when you rotate the dipole against its torque, here no forces act on the dipole. Force is 0. Here torque acts. Okay, when you rotate the dipole against the torque, you see when you rotate it like this. You suppose rotate the dipole in anti-clockwise direction. When you rotate anti-clockwise direction means you are rotating against the torque. Then now you have to do work to rotate it, because dipole will not automatically rotate. It's a stable equilibrium position. It will not rotate. When you rotate like this to this position, then you have to do some work, and your work done will be stored in the form of potential energy. I told you always, work done is equal to change in potential energy. Work done is equal to change in potential energy. When you rotate it against the torque, and when you leave, again it return back to its stable equilibrium position. How much work you have done to take to that position, that much work is again done by the field to take to that position. Okay, so due to that reason, dipole has potential energy, because you are rotating the dipole against the torque. Whenever you do something against the force, against the torque, then potential energy increases. Now let's see what is the potential energy of the dipole. We will rotate the dipole from theta 1 angle to theta 2 angle. If we rotate from theta 1 angle to theta 2 angle, then we have to do work. That work done is equal to change in potential energy between two positions, from theta 1 to theta 2. Okay, work done is equal to change in potential energy. Now see, what is the torque action of the dipole when the angle is theta? Pe sin theta. So this is the torque act on the dipole that already you know in the first chapter, torque on the dipole. Then what is the work done to rotate the dipole from theta 1 angle to theta 2 angle? Is the torque constant? Is it constant? No, it is not constant. If it is not constant, what you have to do? We have to find work done by integration method. When force is not constant, torque is not constant, we have to do by integration method. We have to do calculate work done. So work done is equal to F dot ds. No, now force here is rotational motion. So rotation happens. So in place of force we write tau. In place of s we write theta. Tau and theta. But no dot here, because both will be in same direction. Torque, axial vector along the axis act. Where is the direction of torque? I have told you. D theta also it is axial vector. So both directions are same. So simply tau d theta. And what is tau? Pe sin theta d theta. Integration is from theta 1 angle to theta 2. P constant taken outside. What is the integration of sin theta? Sin theta d theta. Then the integration is, minus cos theta. Theta 1 to theta 2. So this is P minus cos theta 2. First I put upper limit, then minus plus cos theta 1. So it is coming Pe cos theta 1 minus cos theta 2. This is the work done to rotate the dipole from theta 1 angle to theta 2 angle. It's a very important expression. Many numericals will solve based on this expression. Work done P cos theta 1 minus cos theta 2. But our aim was not work done. Our aim was to find potential energy. But work done is always change in potential energy. But how will find potential energy? I have told you. When you start the motion from zero potential energy point, means from infinite. But here it rotates inside the electric field. It's not coming from infinite. It's not a single point charge. So now here you will understand. Not always will bring the body from infinite. I have told you to bring the body from zero potential energy point. It may be infinite. It may be somewhere where potential energy is earlier zero. You can also bring from that point. But by default in physics we are bringing from infinite. But here we will not do. Here we will start rotating the body from a point where potential energy was zero initially. And what is that point? I am telling you that point is, means theta 1 is 90 degree. If we take theta 1, the initial angle 90 degree. At 90 degree the body has zero potential energy. Also we can check, you see. Then what about theta 2? I am taking only theta. Okay. Then work done is equal to potential energy. Now the potential is how much? PE. You put here cos. This is 90. Theta 1 is 90 minus cos theta. So now what is coming? Minus PE cos theta. So this is the potential energy of the dipole in uniform electric field. Potential energy of the dipole in uniform electric field. Now we can check it here. What special cases we discuss? Now see the special cases we discuss here. When theta is 0, what is potential energy? You see, minus P means this condition. This is electric field. This is dipole moment. Minus P, potential energy is minimum. Stable equilibrium position. When a body is in stable equilibrium position, its energy is always minimum. See, potential energy is minimum. Minus P means it's a minimum potential energy. Theta is equal to 90 degree. Cos 90 you put here 0. I have told you. When 90 degree angle, potential energy is 0. For that reason, I have started from 90 degree. Okay, I have brought the dipole from 90 degree to any angle theta. Then I found the potential energy. Okay. Then theta equal to then 180 degree. What is U value? You put here cos 180 become plus PE. Means this is the electric field and this is the dipole moment. Okay. What is the angle between them? 180 degree. So maximum potential energy, unstable equilibrium position. You recall the first chapter we have discussed. When theta is 180 degree, that is unstable equilibrium position. Equilibrium but unstable. Maximum potential energy the body will have. So this is about potential energy of the dipole in uniform electric field. Now we will discuss potential energy of two particle system. Potential energy of Q1, Q2, R1 to separation. Potential energy of two particle system. Already I think I have told you about two particle system. You may tell, sir, already I have discussed. We have discussed already. What is the expression? K Q1 Q2 by R1 2. No, we will discuss now potential energy of two particle system in external electric field. I just attach again some terms there in the heading. Potential energy of two particle system in external electric field. Then what was the earlier case? In earlier case there was no other electric field. Q1 was there alone, Q2 come, then that is the potential energy of two particle system. But now I am telling you potential energy of two particle system in external electric field. Means earlier electric field is here, this region. In this region now here is one electric field, earlier one electric field is here. Suppose this point has potential V1. Now Q1 is there. This V1 potential is not of Q1. V1 potential is of the field which is earlier present here, and Q1 is placed there, and at a point potential is V2. To which charge is placed there? Q2 is placed there, and separation between them is R1 2. So this potential V1 and V2 are of the external field, not of Q1 and Q2. Okay. Now what is the expression? It's a very important one. Okay. So now we bring Q1. When you bring Q1, initially Q2 was not there. First we bring Q1, our procedure from infinite to the position. When you bring Q1 from infinite to the position, work is done or not? Now work is done. Why? Because earlier electric field was there. So some work is done. So how much work is done? W1 I have told you the formula of work done when you bring a charge from one point to another point. W is equal to Q into del V. So here Q1 into del V. So Q1, what is del V? Final position is V1, and what is the initial position? Infinite. We bring this Q1 from infinite to this position, and here potential is V1. From V1 minus infinite. And what is V infinite value? 0. So this is Q1 V1. This is the potential. This is the work done to bring Q1 from infinite to this position. This happens because earlier external field was there. To which point it is brought, there was some potential, that is V1. Now when I bring Q2, what is the work done? I have to do 2 work. How? One is against Q1, one is against the field. Which field is there present? And at that point, what is the potential? V2. Similarly, for the field, what is the work done? Q2, V2, like this. And for Q1, what is the work done? K, Q1, Q2 by R, 1, 2. So what is the potential energy of the system? Q1, V1 plus Q2, V2 plus K, Q1, Q2 by R, 1, 2. So this is the potential energy of two particle system in external electric field. Okay. So after this, you can solve one important example in your NCERT book. Example number 2.5. 2.5 example is based on this. It's a very important example. Difficult example always comes in exam. You can solve that example. And also you can solve 2.3 example, 2.4 example. So these 3 examples, after completely listening this video, you can solve these 3 examples of NCERT book. These 3 are very important examples. 2.5 is the rarest one and always comes in exam. Thank you.